So we got this circuit going on, and we've got a couple initial conditions, but don't worry about that yet. Yep, come on, where's my pen? There. Don't worry about that yet. We just want to set up the equations and get the particular solutions. So this will be an equation in terms of, well, the KCLs, they have to sum to zero. All the currents have to sum to zero, so we express things in terms of voltage. Current through the resistor is V over R. Current through the inductor is the integral of V over L. You've got the current when time equals zero, and that will be a non-zero value now. So this is, anyway, we'll get to that in a second. And then the capacitance times differential voltage with respect to time is the current through the capacitor. They got to sum to zero. Okay, rearranging the equation, differentiating, and then dividing through by, dividing through by C, we get this equation next. Given the values of C and R, 2 times a fifth is 2/5. Reciprocal of that is 2.5. LC is going to be exactly 1. And now we find all of our values. The omega n is the square root of 1, and 2 zeta omega n equals 2.5. Let's see, 2 zeta omega n equals 2.5. I don't know if I believe that value of zeta. Zeta should be 2.5 divided by 2 times omega n, or 2, which is, it should be 1.25. I think the book has an error right here. I think that's supposed to be 1.25. Okay, all books have errors. Just remember that. It won't change our analysis much. In fact, I think this equation is absolutely correct. Getting the roots of S. Let's see, 2.5 squared is 6.25 minus 4. 6.25 minus 4 is 2.25. Root 2.25 is 1.5. So this is actually correct when you work out the math. Okay. Then you're given this, and this is where we need these two things right there. We've got VC of 0 up here, which is fine. We've got IL of 0. How are we going to get the derivative dV dt of 0 given, this information here? So that's the trick with this problem, and we can solve it. VC over R, VC of 0, we know that. So that's 4 divided by R, which is, let's see, 2 ohms. And they have to divide by C also. R C. 4 volts over R C to get to here. And the negative sign because it's on the right hand side of the equation. IL, there's IL right up there. Negative sign, negative, negative. So IL is negative here, and we're taking it to this side of the equation, so it becomes negative, negative. Got to divide by C also, right there. Got to divide everything by C. And plug and chug, and we get numbers. 5 and, oh, excuse me. 5 is the number we need for dV dt equal at 0, and 4 is the number we need for Vc equals 0. So, dV dt, negative 5, V, negative 4. Now we just take this equation and make sure that at 0 this is true, and at and the derivative at 0 this is true. So K1 plus K2 has to equal 4. The derivative, negative 2K1, negative half K2, has to equal negative 5. 2 equations, 2 unknowns, pretty simple linear algebra type solution. And voila, we got the answer. Okay, strategy. Good idea to talk about that. How are we strategizing it? Write down the equation, the model. I always say step 1 is draw the circuit, sketch. Get your characteristic equation, solve it for all the various parameters, get the roots, there's the roots, form of the solution. You don't know K1 and K2 yet, but at least you know that much. And then the rest of it's finding the constants. Don't forget information up here like so. Don't forget that. To find the constants. This is what you need to figure out what the constants have to be. One more thing I wanted to say. This trick right here. We just solved for dV dt equals 0. We knew everything else. Okay. At 0, what's true? Well, at 0, current through the inductor is that. At 0, time equals 0, this integral is 0. You're integrating from 0 to 0, which makes 0. So we just solve for dV dt and rearrange the equation, plug in numbers, and get our answer. And then take the form of the equation and at time equals 0 and the derivative of the equation at time equals 0 to get our 2 constants. Okay. You might have to find this. That's okay. It goes with the territory. Okay, that's it. MATLAB. This is what the circuit does, how it responds. So let's take a look, a step back. This is an overdamped situation. Zeta is bigger than 1. I think it's 1.25, not 1.5. I disagree with the book on this, but it doesn't matter. It's still bigger than 1. So we're going to have a response that looks like this. Okay. End of discussion here. It's your turn. The rest of the rest of this chapter, I want you to do the examples just like you do them in class. Don't skip them. You have the handouts, you have the slides, the handout slides. So you have the answers sitting in front of you. They're examples to help you figure things out. Do it. Even if we can't meet and talk about it together, I'm going to be available at office hours. I'm going to be available at the times that classes meet. So get together, talk about this stuff, and work these examples on your own. I've gone through everything I can say about it, giving you all the background. Now it's your turn. One trick with this guy, let's see, is this the one where I think there's a trick that, no, this isn't the one. It's one that's a little further on that's kind of tricky. This isn't so tricky. This is this is almost like the previous example that I just showed. The next one is tricky. So I'm going to give you a hint. Even though I want you to do it, I'm going to give you a hint. Use KVL around here, the blue. So you'll have this equation. Use KCL at this point. So you'll have this equation. And you have to rearrange things a little bit. Get everything all together. So here's I. Make the substitution right there. Here's another substitution right there. And then it's algebra, get all the factors together. You can read it yourself. You can see basically that it's going to work because you're going to get the second derivative of voltage and then a bunch of algebra calculations to get this coefficient, A1, then a bunch of algebra calculations to get this coefficient, A2. Once you're here, you're practically done. Okay, I am going to stop here, and this is it on Chapter 7. And I'll be available to talk about it.